This is a short tutorial on stoichiometry, which is the use of quantitative techniques to solve chemical problems. Students often don't understand why being able to do stoichiometric calculations is really important. So I've made up this example to show you how stoichiometric calculations go beyond just the chemical laboratory. So here's a word problem for you. An infant has a bacterial ear infection, and a doctor prescribes an ampicillin dose of 20 milligrams per kilogram of body weight. The baby weighs 14.7 pounds, and the antibiotic comes in a solution that has a concentration of 150 milligrams per 100 milliliters of solution. How many mils should the pharmacist tell the mother to give the baby with each dose? Well, that's a commonplace problem that is outside of the chemical laboratory, but it is still stoichiometry. Well, let's take a look at how we're going to do this calculation. Whenever we do stoichiometric calculations, we're always going to start over on the right-hand side of the piece of paper with an equal sign and the units of what we want for final answer, in this case, mils of antibiotic. Once we've done that, we're going to start out on the left-hand side with what we know based on the word problem, which is that we've been prescribed 20 milligrams of antibiotic per kilogram of baby. Okay, let's look at what's in the numerator. In what we know, we have milligrams of antibiotic, and we'll need to convert that to milliliters of antibiotic solution. But our final units don't have anything in the denominator. We have to find a way to get rid of kilograms of baby weight. Well, we have been given information in the problem on baby weight, but it's in pounds. So the first thing that we're going to need to do is convert kilograms of baby into pounds of baby. And we're going to do that by multiplying by a conversion factor that we can easily look up on the internet of kilograms to pounds. And the conversion is 1 kilogram is 2.2 pounds. Well, we could write this conversion factor either way, either with pounds in the numerator or kilograms in the numerator. But because our starting information has kilograms in the denominator, we'll have to use this conversion factor with kilograms in the numerator so that kilograms can cancel out. At each step in this solution, we're going to physically cancel out the units that we're trying to get rid of so that if we accidentally flip this conversion factor, we're going to catch it. All right, so now I have units of milligrams of antibiotic per pound of baby, and we do know how much the baby weighs in pounds. That's 14.7. So because we have pounds in the denominator, we will multiply by baby pounds. That will allow us to get rid of baby weight in this problem. And right now, if I stop and look at the units that I have milligrams of antibiotic. Ultimately, I need milliliters of antibiotic. We do have a conversion factor between milligrams and milliliters. Um, we've been told that the solution comes in 150 milligrams per 100 milliliters, but we're actually going to have to reverse this conversion factor because we currently have milligrams in the numerator. It needs to go away, so we're going to need milligrams of antibiotic in the denominator. And for a final answer, we need milliliters of antibiotic, which means that we have to have milliliters in the numerator in our conversion factor. Again, we'll physically go ahead and cancel out units so that we can see that we haven't accidentally flipped that conversion factor. Of course, it was given to us flipped 150 milligrams per 100 milliliters, but we can use that in either direction, and this problem requires us to use it as 100 milliliters per 150 milligrams. We can see the only units we have left when we're done with the calculations are the units that we need for our final answer, which are milliliters of antibiotic. Well, let's see how that type of philosophy applies to the stoichiometric calculations that we need in chemistry. Well, the first thing we all need to acknowledge is your high school algebra teacher was correct. Life comes at you as word problems. We've just seen that with the previous example. And it's not just chemistry, but it's everywhere. The vocabulary that we use in chemistry for the quantitative aspect of chemistry is stoichiometry. To do stoichiometry and stoichiometric calculations, the first thing we require is a balanced chemical equation. Hopefully, you've already reviewed that video. If you have not, please go back and take a look at that. These balanced chemical reaction predict the results of reaction, but require some math. And this shows the balanced chemical equation for the oxidation of iron. Your car in your driveway right now is busy forming rust. The iron is oxidizing. And the big numbers in front of our reactants and products are our stoichiometric coefficients that balance the equation. And we need to have these stoichiometric coefficients to do our stoichiometric calculations. These stoichiometric coefficients represent either mole ratios, or they can, at the atomic and molecular level, they can represent molecular ratios or atomic ratios. All right, so let's talk about molecules versus moles for a minute. Balanced chemical equations tell us about molecules, atoms, or moles. So this balanced chemical equation for the oxidation of magnesium can be looked at two ways. We can first look at it at the microscopic view at the level of atoms and molecules. This balanced chemical equation tells us two atoms of magnesium will react with one molecule of oxygen to produce two molecules of magnesium oxide. Heat is also sometimes shown as a reactant or product. In this case, we can actually burn magnesium in the air. It will actually burst into flames to produce magnesium oxide. In terms of calculating heat, we'll wait until we get to the chapter on thermodynamics. This balanced chemical reaction can also be viewed at the macroscopic level of grams and moles. This balanced chemical reaction tells us that 2 moles of magnesium, which is 48 grams, will react with 1 mole of oxygen, which is 32 grams, to produce 2 moles of magnesium oxide. Well, I'll leave you to calculate on your own what mass of magnesium oxide is produced if we react 2 moles of magnesium with 1 mole of oxygen. Well, balanced chemical reaction tells us about moles. So we should remember that this tells us moles of magnesium reacting with moles of oxygen to produce moles of magnesium oxide. But in the laboratory, we weigh out on the balance grams and work with gram amounts of materials. So if we ask ourselves the question, how many moles of oxygen are required to completely react with 10 grams of magnesium? The only way we can find that out using a balanced chemical reaction is by drawing ourselves a roadmap. Well, we know from the balanced chemical reaction how many moles of material react with each other, but we've been given grams of magnesium. We're going to have to start our calculation by converting grams of magnesium to moles of magnesium so we can use our balanced chemical reaction. And then finally, we've been asked to find out how many grams of oxygen are required to react with that number of grams of magnesium. Well, we're always going to start on the right-hand side of the page with the units that we need for our answer. We've been asked to find grams of oxygen. Then we will start on the left-hand side with what we know. We know that we're starting out with 10 grams of magnesium. Our roadmap tells us that our first step is to convert grams of magnesium to moles of magnesium. We'll do that by multiplying by 1 over the gram molecular weight. We'll make sure that we cancel out our units of grams. And what we have right now are the number of moles of magnesium when we've weighed out 10 grams of magnesium. Well, our roadmap tells us that we next need to convert moles of magnesium to moles of oxygen. That's the molar ratio, 1 mole of oxygen to 2 moles of magnesium. Magnesium cancels out. And now we know how many moles of oxygen we need if we're going to fully react 10 grams of magnesium. Well, we've been asked for grams of oxygen, not moles of oxygen. So we're going to have to multiply by the gram molecular weight of oxygen. Moles of oxygen cancels out. And now the only units we have left on the left-hand side of the equal sign are grams of oxygen. Well, that's what we were asked to find for an answer. Our units check out. We can now grab a calculator and chug through this calculation. Well, once we've found that, the next question that we probably want to know is how many grams of magnesium oxide will be formed if we have 10 grams of magnesium and the proper number of grams of oxygen. Well, again, we need to draw ourselves a roadmap where we'll need to convert moles of magnesium oxide to grams of magnesium oxide. We're going to follow this roadmap one more time. We're going to start on the right-hand side with units of what we need, grams of magnesium oxide. Then we'll start on the left-hand side with what we know, grams of magnesium in the reaction. The roadmap tells us the first thing we need to do is to convert grams of magnesium to moles of magnesium. That's 1 over the gram molecular weight. We now know how many moles of magnesium we've got. Taking a look at the balanced chemical reaction, we know that the molar ratio between magnesium and magnesium oxide is 2 to 2 or 1 to 1. So we're going to multiply by the molecular ratio. We now know how many moles of magnesium oxide will be produced. We're asked for grams of magnesium oxide. So we will multiply by the gram molecular weight of magnesium oxide. Moles of magnesium oxide cancel out. The only units we have left on the left-hand side of the equation are grams of magnesium oxide, which is what we were asked to produce for a final answer. Well, let's try a different problem. Your body metabolizes 10 grams of glucose and produces carbon dioxide and water. How many grams of oxygen does your body require to complete this reaction? And then how many grams of carbon dioxide are produced that your body will have to exhale through your lungs as a result of this reaction? Well, let's go ahead and actually balance the chemical reaction this time. I have 6 carbons as reactant, 12 hydrogens as reactants, and from glucose, I have 6 atoms of oxygen. From O2, I have 2 additional atoms of oxygen. On the product side, I have one atom of carbon, 2 atoms of oxygen in my CO2. On the water side, I have 2 atoms of hydrogen and 1 atom of oxygen in water. Well, as we look at this reaction, we see if we're going to play around with a stoichiometric coefficient in front of glucose, we will constantly change carbon, hydrogen, and oxygen whenever we change the stoichiometric coefficient. On the other hand, if we look at our O2 molecules, if we play around with a stoichiometric coefficient of O2, the only thing we're going to be changing is oxygen. All right, so the strategy we're going to use here is to first balance carbon and then hydrogen, and then we'll play with the stoichiometric coefficient in front of oxygen to balance out the reaction. All right, glucose has 6 carbon atoms. Carbon dioxide, which is the only place on the reactants I have carbon, comes in units of single carbons. So I'm going to multiply carbon dioxide by a stoichiometric coefficient of 6. That gives me 6 carbons as reactants, 6 carbons as products. So my carbons are balanced. But when I multiplied CO2 by a stoichiometric coefficient of 6, I produced 12 atoms of oxygen. We'll have to keep track of that. Let's move on to water and balance our hydrogens. Hydrogens in glucose comes as 12 atoms. Hydrogen in water comes in units of 2. To get my 12 hydrogens as products, I will have to multiply by my water by a stoichiometric coefficient of 6. This gives me 12 hydrogens as reactants and 12 hydrogens as products. Carbon and hydrogen are now balanced. When I put that stoichiometric coefficient of 6 in front of the oxygens, however, in front of the waters, I produced 6 oxygens. All right, carbon and hydrogen are balanced, oxygen is not. Let's see what we've done on the product side. We've produced 12 oxygens in carbon dioxide, 6 in water, for a grand total of 18 atoms of oxygen. Well, on the reactant side, I have 6 oxygens as part of glucose. Well, the first thing that I want to do is I want to subtract those 6 oxygens from the 18 on the product side, because I don't want to change the stoichiometric coefficient in front of glucose. This means I still have 12 oxygens on the product side unaccounted for. Well, the place that I'm going to pick up those oxygens is from O2, and we will see that oxygen atoms on the reactant side come in units of 2. So I'm going to take that 12 required oxygen atoms on the product side, divide by 2, and see that I need 6 O2 molecules to provide that 12 oxygen atoms to balance out my chemical reaction. So I have balanced both sides of this chemical reaction. 1 glucose molecule will react with 6 oxygen molecules to produce 6 molecules of carbon dioxide and 6 molecules of water. Or 1 mole of glucose will react with 6 moles of oxygen to yield 6 moles of carbon dioxide and 6 moles of water. All right, we're always going to start our calculations on the right-hand side of the page with the units that we need for a final answer, which are grams of oxygen. We know we're starting out with 6 grams of glucose. We're going to have to convert grams of glucose to moles of glucose. We now know the number of moles of glucose we have when we have 10 grams. Well, we don't need moles of glucose, we need moles of oxygen. We're going to multiply by the stoichiometric ratio of 6 moles of oxygen to 1 mole of glucose, canceling our units as we go along. We're then going to convert moles of glucose to moles of oxygen to grams of oxygen by multiplying by the gram molecular weight. On the left-hand side of the equation, the only units we have are grams of glucose. That's what we would like for a final answer. So we're good to go. We're going to grab a calculator and chunk through this calculation. Well, how many grams of CO2 are going to be produced by this reaction? We're going to start with the units that we want for final answer, grams of CO2. We're going to go through the same process of converting grams of glucose to moles of glucose, multiplying by the stoichiometric ratio of glucose to carbon dioxide, which is 6:1. We'll know how many moles of CO2 are produced. We'll multiply by the gram molecular weight to find out how many grams of CO2 are produced. Since we have grams of CO2 on the left-hand side of the equation, grams of CO2 was our target, we're ready to go ahead and grab a calculator and go through this calculation. Now, there's a hidden assumption in this problem that we probably should talk about. And anybody who's ever worked out in the gym lifting weights, which is an anaerobic exercise, not aerobic exercise, knows that we assume that we have sufficient oxygen for this reaction. If our exercise goes anaerobic, we don't have enough oxygen present. In fact, this reaction diverts and glucose does not oxidize all the way to carbon dioxide. It goes to lactic acid, which then cramps our muscles. Well, let's try one more problem, this time with liquid volumes, which will give us an exercise again in drawing these roadmaps and doing more complex calculations. So your car runs on gasoline, not glucose. For ease of calculation, we're going to assume that gasoline, which is a mixture, is entirely present as the molecule octane, C8H18. Octane burns in your engine to form carbon dioxide and water, just like glucose burns in your body to form carbon dioxide and water. Well, let's go ahead and balance the reaction then of octane reacting with oxygen to give us carbon dioxide and water. Well, just by inspection now, we see on the left-hand side, we have 8 carbons. We need 8 carbons on the right-hand side. So we're going to multiply carbon dioxide by 8. We have 18 hydrogens on the left-hand side. We need 18 hydrogens on the right-hand side. We're going to multiply oxygen. We're going to multiply hydrogen, the water molecules, by 9 to give us 18 hydrogens. Now we have a problem. We have 8 carbon dioxide molecules giving us 16 oxygens. We have 9 water molecules giving us a further 9 oxygens. When we add those together, we need 25 oxygen atoms. But oxygen as a reactant comes in units of 2. Well, I've chosen to write a stoichiometric coefficient of 25 divided by 2 on the left-hand side. Since I'm only worried about math, that's perfectly allowable. Of course, I can't have 25 divided by 2 oxygen molecules because I can't have half a molecule. So if I'm worried about the molecular realities, I can't have 25 divided by 2 as a stoichiometric coefficient. If I'm just worried about the math, then that's perfectly fine. Okay, so if I start out with 1 gallon of octane that I've gotten out of my gas pump, how many grams of the greenhouse gas carbon dioxide will we produce from that 1 gallon of octane? Well, of course, again, we're going to start by drawing ourselves a roadmap. We know that our balanced chemical equation tells us about moles, not grams or gallons. We do know that we're being asked to finally come up with an answer of grams of carbon dioxide. But the other half of this roadmap, usually we start out with grams, and we've not been given grams. We've been given a volume of a liquid. Well, if we know the density of octane, which we can look up on the internet, we know that we can convert grams of octane into mils of octane. Well, that only partially gets us where we want to go because the liquid measurement we've been given is gallons, not milliliters. Well, again, we can look up a conversion between gallons and liters, and then we'll also have to do a conversion from liters to milliliters. But ultimately, this is the map that we're going to follow. As always, we're going to start out on the right-hand side of the page with an equal sign in the units of what we need for a final answer, grams of carbon dioxide. Then we'll start out with what we know at the beginning of the problem, which is gallons of octane. Well, our map tells us I'm going to have to convert gallons, an English unit, into milliliters, which is an SI unit. The first thing we'll do is multiply by a conversion between gallons and liters. Liters on the top, gallons on the bottom, so gallons cancels out. And then we'll multiply by the conversion factor from liters to milliliters, liters on the bottom, so they cancel out. And if I stop right now, what I have is the number of milliliters when I have a gallon of octane. Well, we've got the density, which will allow us to convert milliliters into grams. Milliliters cancels out. Now I know how many grams of octane I have when I have 1 gallon. Well, our map tells us that we need to convert grams of octane into moles of octane. That's 1 over the gram molecular weight of octane. Now I know how many moles of octane I have when I have 1 gallon of octane. Well, the roadmap tells us we need to convert moles of octane into moles of carbon dioxide. That's a stoichiometric ratio of 8:1, 8 moles of carbon dioxide for every mole of octane. Now I know how many moles of carbon dioxide will be produced from 1 gallon of octane. Well, I'm asked for grams of carbon dioxide, so we're going to have to multiply by the gram molecular weight of carbon dioxide. The only units I have left on the left-hand side of the equal sign are grams of carbon dioxide. That's what I wanted for an answer on the right-hand side of the equal sign. So I have the equation set up right, and I can grab a calculator and go ahead and grind through this problem. Just as a practical sense, what happens if we don't have enough oxygen present to completely react the octane? Well, the chemical reaction will stop at elemental carbon, which we see as soot, either in our tailpipe or in our chimneys from our wood burning stoves. And the reaction path changes to a different reaction.